welcome back. Today we will continue with the more modeling aspects of thermodynamic assessment. This is what we are going to see today, Gibbs energy modeling with more concepts on sublattice formalism and how to model short range order. We said these are the different terms that we need to understand in sublattice formalism. We'll see them one by one today. We have introduced a couple of these terms already. In this AB compound that we saw in the last class, we said we have two sublattices in this. One sublattice has constituent of only A and the other has only B. So now what is there in the sublattice? A or B. These are the constituents. Constituents means this, the species inside each sublattice. Right? Then two sublattices with equal relative number of lattice sites. These are the relative number of lattice sites here, 0.5, 0.5. Two terms are introduced already to you. Now we will see more. To understand the other terms, let's take the example of a non-stoichiometric compound like ALNA. Non-stoichiometric in the sense that it has a homogeneity range, right? So G versus X curve can look like this for that kind of a phase. AB, let's say, this is a non-stoichiometric phase, meaning it's not a line compound, it is stable over a range. This is at a particular temperature where you see Gibbs energy curve of another phase alpha and the compound of our interest AB, non-stoichiometric phase. So these two are having Gx curves like this at some temperature, and you can see between A and B, these 2 points where the common tangent touches, between these overall compositions we will have two phases, alpha and AB, and between C and D also we will have alpha and AB, two phases, right? But between B and C we will have a single phase AB stable. So this is a range of composition over which AB is going to be stable, right? So this is what we want to model now. The sublattice formalism is chosen like this: A comma B, A1, A comma B, A2. So since this is going to be AB type, we can keep this as 0.5, 0.5 also, but A1, A2 is given basically to show you a generic view of what is relative number of lattice sites. Now each sublattice has both elements AB, AB, right? This is important in order to give this homogeneity range. Let's see how it comes. A and B are the constituents, straightforward. A1 and A2, the small A1 and A2 here are relative number of lattice sites. Then constituent fraction or site fraction. What is this site fraction? In each sublattice, we can keep on varying the amount of A and B to achieve various compositions. So what is the composition of an element within a sublattice? Let's say mole fraction of constituents in a sublattice. That is what site fraction is. So if you are puzzled about what is this new term site fraction, you just treat it as mole fraction but within a sublattice. A sublattice has multiple species in it. You can keep the summation of all of them to be equal to 1, so that each species has a mole fraction kind of thing, and that is called site fraction. Okay, mathematically we have this yi, s, we use x for mole fraction and y for site fraction for element I in sublattice S. Okay, that is equal to NIS divided by NS. YIS, which is site fraction of constituent species I on sublattice S. So we want this. To do that, we need these two numbers, number of sites occupied by that particular species I in sublattice S divided by the total number of species on sublattice S. Right. Now comes one of the most important ideas in sublattice formalism, that is constituent arrays. Let's understand them keeping this AB type of sublattice. We are writing a constituent array here, I0. This is 0th order constituent array. So this I is the symbol used for that, and different things are written here. Combinations of species from sublattice 1 and 2 come here. The colon separates what is there in sublattice 1 to the one in sublattice 2. The colon separates the element coming from sublattice 1 and sublattice 2. Okay. So now from sublattice 1, A is taken, from sublattice 2, A is taken. So this AA represents certain composition, that is 100% A. You can sense that if you take a compound of this sort, A occupying the full sublattice here and A occupying the full sublattice here, if these two sublattices interpenetrate, what you get is 100% A in this structure, this AB phase sublattice, right? So that is this particular composition. Similarly, different compositions can come, A in sublattice 1, B in sublattice 2, or B in sublattice 1, A in sublattice 2, and B in both the sublattices. If this is the case, then in this space, which compositions we will cover? You can imagine these three different G values will come. This is AA, this left extreme one, that will give the Gibbs energy of this one. And BB is this composition, with that we will get the Gibbs energy of this one. So AB compounds Gibbs energy with 100% B and 100% A, and these two are similar because occupancy is 0.5 in both the sublattices. A, B or B, A, both these things will represent the composition in the middle, this one, and this is the Gibbs energy we are targeting by modeling this, right? And second, or I1, meaning the constituent array, second constituent array will have mixing in each sublattice. You see, first sublattice has A comma B colon A. So we are allowing mixing in first sublattice. It means that the composition of the side fraction of A and B can keep changing, so that we will achieve different compositions. If you see, A in the second sublattice is fixed, that is about 50%, right? So we will keep A here and keep changing A and B in the second 50%, the first 50% will keep changing A and B. Okay, so if you keep changing A and B, what will happen? If you keep B as 50, you will be in the middle. A is already 50. Then if you keep decreasing B, you will be covering this entire composition, achieving complete AA. Okay, so this particular mixing in first sublattice covers a big range of composition. Okay, that is taking care of mixing. Okay, similarly we have different mixing terms coming. I2 also would be similar, and of course this is just a binary AB, so these things may be repetitive in the sense that they may cover the same composition again and again. So but when we go to higher order systems, you will see the use of this kind of arrangement. So the mixing is like this. You see, in the first sublattice where we had only nickel atoms, there aluminum is replacing some of the nickel, and nickel is replacing some of the aluminums in the other sublattice. So this is how the mixing in each sublattice is expected. Of course, the 100% AA or 100% BB can never happen in nature in this particular structure. These are called fictitious N members. Okay, so N member, the word is used for these things because they are the ones which will dominate the Gibbs energy. We'll talk about that in the next slide as well. This is the ABCD phase. ABCD, this is how the sublattices are, and constituent arrays are written like this. So in order to understand this, we can visually see some composition space of these different things. If you see the corners, they are all of this particular first constituent array, where you see AC in this corner, and from there this corner is AD, and from here to here when we go, what happens is AC becomes AD, therefore in the second sublattice C is replaced by D. Along this line, what happens is C and D both mix in the second sublattice. So various compositions of C and D can come from here to here, reaching 100% D here in the second sublattice. Okay. Similarly, all these edges are going to represent mixing in one of the sublattices. And the red line here, this red line here, they are going to represent mixing in both the sublattices. If you see here, AD is here and AD becomes BC. Therefore, in the first sublattice, A is gradually replaced by B across this line, and D is gradually replaced by C across this line. Therefore, eventually it becomes B colon C. Right? So, this is the composition space covered by this arrangement of constituent arrays. Now, what is important here is these corner values. The composition in these corners, for those, they look like a compound, like A and D joined together to form a compound, right? So these compounds, they are called as end members, and the Gibbs energy corresponding to them will be multiplied by less number of mole fractions, because there are only two elements. They will be multiplied with less number of mole fractions, whereas these lines or these lines, across them you will be having more mole fractions coming to the contribution of this mixing and all, that will be multiplied by more mole fractions. Therefore, the most significant contribution to the Gibbs energy of this particular phase will come from these compounds. These are called as N members, and they contribute the most to the Gibbs energy. Since I0, the zeroth order constituent array, also known as N members, resembles compound, and it is the most significant contributor to the Gibbs energy of the phase. The sublattice formalism here is called as compound energy formalism, CEF. Okay, so these sublattices that we use, instead of that, people use CEF, compound energy formalism term. So don't be confused, it is essentially sublattice formalism. Because of this reason, it is called as compound energy formalism. Okay, so these are the different terms that we wanted to understand about sublattice formalism: constituent array, N members, compound energy formalism, side fractions. So all these things we have covered now. So if you look at a model, you have to understand these different terms. How many sublattices are there? What are the constituents there? What is the relative number of side fractions? How the constituent array will look? All these things are important. Certain N members can be fictitious totally. So certain N members can be fictitious in the sense that, if you look at the previous example, we said in AB structure 100% AA and 100% BB, right? The first constituent array, if you look at, 100% A came when we arranged both the sublattices to have AA, right? If that is there, mathematically we are able to put that. Can it be there in reality? The answer is no. 100% A containing AB kind of structured phase is not possible. So that is a fictitious one. But mathematically we can deal with such things. And that is important also in order to have the complete curve. Okay. So how to get the Gibbs energy of that is a more tricky thing, and that can cause a lot of problems in the optimization. But one has to be careful about this aspect, that it is a fictitious compound. Right, so that is about sublattice formalism. This model in its general mathematical form does not assume any specific crystal structure. You see, we are imposing it from the outside. The structural conditions are not built into the model itself. They have to be added from outside. We understand that it's a B2 structure, two different sublattices are there, how their atoms are arranged in each of them. We understand things, and then we formulate the sublattice in such a way that it resembles the reality. So this is something that is imposed from the outside. Okay, we need to know the crystallographic information for this. Therefore, it is to be collected during the input data collection or the experimental generation of input data. We need to keep a track of what are the crystal structures of different phases. And that crystal structure information is mainly used for deciding the number of sublattices to be used and for assigning constituent species into each of them. So crystal structure has more layers to that. We will come to that when we see sublattice formalism of some compounds. Okay, this is a summary of what we have seen till now. Constituents are straightforward. Constituent array is just a way of listing which atoms or species can sit on each sublattice. We usually write the whole set as I, while a single species is written as small I. This is a capital I, this is a small I. If needed, we add a superscript S to show which sublattice that species belongs to. And these arrays can be having different orders, I0, I1, I2 and so on. The 0th order ones are called as N members. And the term compound energy formalism is another name used for sublattice formalism. The reason is that most important contribution to the Gibbs energy through this formalism comes from the N members or the 0th order constituent array. Okay, the N members that resemble compounds. That's the reason why we are putting the word compound energy formalism. Now, we already told that the sublattice formalism can be used not only to model compounds and the compound with some homogeneity range. It can also be applied to solutions. Now we will see different solutions. First we will start with interstitial salt solution, where we have this kind of sublattice. This is basically AB, two large sized atoms, let's say iron nickel kind of things, and in that carbon is dissolving in the interstitial sites. Va stands for vacancy. If that is the case, we can model it like this. This C can be any interstitial element here. Okay, so A and B substitutional element, C is an interstitial element, for example carbon. Okay, so now why we have 1 here and 3 here? This is also important to understand, because each atom has 4 tetrahedral subcells if the space around it is divided. Okay, therefore 3 of them are imagined to be occupied by vacancies. Therefore the sort of ghost sites. Okay, so they are having vacancies, and the carbon occupies such site, these 3 vacancy sites. That is where carbon can also dissolve. Okay, the remaining thing 1 is for the atom in the lattice site. Okay, this is why we put 1 and 3 here. What about the other solutions, liquid and substitutional solid solutions? We can have only one sublattice and mix all the elements in that. But most of the times vacancy is considered as a separate sublattice in substitutional solid solution. This is to engage the extrapolation, let's say to higher order systems where possibility of interstitial elements come. Also in configurational entropy it has a role to play. Now let's look at a compound. Deciding number of sublattices, constituents, relative number of lattice sites cannot be always straightforward, as in the case of AlNi. There we had only aluminum in one sublattice and nickel in one sublattice. It was straightforward to model the sublattice also right from the directly from the crystal structure. But in many cases it will not be straightforward. There what we will need to do is to consider Wyckoff positions. That is, Wyckoff position means a set of symmetry equivalent points within a crystal structure. Symmetry you may be knowing if you have done any crystallography content in any of the courses. Symmetry is basically about if you take a cube and rotate it 90 degree, you will still see the cube. Okay, for every 90 degree rotation, the cube will remain as the same cube without any change. So that is fourfold rotation symmetry for a cube. So similarly, different types of symmetry elements are there for different crystal structures. And for every lattice site also we can identify what are the symmetry elements that are there surrounding this particular lattice site. So that kind of points are identified, that can be a useful information to decide the sublattices. Okay, then coordination numbers, which are basically number of nearest neighbors. This also we can consider which are the lattice points that have same number of nearest neighbors. They can all be grouped, and that can be called as one sublattice. Different ways. For example, sigma phase. Okay. Sigma phase appears in different systems such as iron chromium, cobalt chromium, chromium manganese, and so on. So for if your alloy happens to have these different elements, then there is a possibility of sigma phase formation in the alloy. In that cases, it is important to model sigma phase, and people have used different sublattices like this. You see 3 sublattices here. Total there are 30 atoms. Okay, it's a big unit cell. So for 30 atom unit cell, how do you model? How do you create the sublattice? Okay, this is tried by a few people. This is also tried by a few people, and this is also recently reported 5 different sublattices. Okay, let me show how is the crystal structure of sigma. I'm opening this software called Vesta. Okay, this is a free software. You can use this, and you have to download a file called CIF file, crystallographic information file, and this file has all the crystallographic information about different phases. Okay, so this is available in open source repositories such as this materials project and all. You can download them and use. I have chromium iron sigma phase structure. Let me show that. Okay, so this is how the crystal structure looks. There are atoms sitting like this. If I rotate it, you can see how complex the structure is. It's quite difficult to identify just in like the case of AlNi, what atoms are sitting where, in what manner we can model them and all. So this is where it is important to identify what are the Wyckoff positions and what are the coordination numbers for each atomic site. Once we do that, we have some clue about how to model the sublattices. And this is how the Wyckoff positions are. A, F and all are some random numbers associated with the Wyckoff positions. Basically to say that okay, two atoms are having A type of Wyckoff positions. Okay, so these are the different types we have, and coordination numbers are here. If you see 8i, 8i, about 16 atoms have I type of Wyckoff position, but 8 of them have 14 coordination number and the other 8 have 12 coordination number. So this is the reason why 5 different types of atomic arrangements are identified, and one of the reports uses 5 different types of sublattices. But in the others it is in a way grouped, and 8, 4, 18, that is the kind of relative number of sites used in these sublattices here. Okay, but each of them can give slightly different results. There can be some advantages and disadvantages. Some may be very accurate but computationally intensive, difficult to optimize. Things like that can be there. There is a degree of subjectivity there, but that is part and parcel of thermodynamic assessment. So all this thermodynamic assessment, in the next couple of classes you will see there is a huge role for subjectivity there in doing the optimization. So experience and skill is really important. A lot of judgments are to be made. That's about the sublattice formalism for compounds. Now we will see how short range ordering is modeled. What is short range order? We have seen that previously when we talked about physical metallurgy and applying thermodynamics to materials. In all those times, we talked about delta H being slightly negative in a solution where there will be more number of AB bonds than the random solution. We call that as short range ordering, right? So there is slightly more liking between A and B atoms, and that causes short range ordering. Now, this short range ordering can happen also in liquids. In liquids, if there are multiple species, some of the species can form some kind of a attraction between them and get into some kind of a compound formation or some associates formation, things like that. Okay. For to model them, associate solution model is used for short range order. For example, in hydrogen oxygen system, okay, this is a gas system where we see these different G versus X curves at 500 and 3000. Okay, Gibbs energy at 500 and 3000, including all possible molecules. Meaning this is for the entire system. Okay, that is constituents. All possible molecules in the sense H, O, H2, O2, H2O, all the different species that are possible within these two, and all of them actually form. So mixing all of them, what is the Gibbs energy? That is plotted here. Okay. A strong V shape appears at 500 Kelvin is due to the formation of the molecule H2O. Okay. At 3000 it is not stable. So at 500 it is stable, and that H2O, you can see this is 2 hydrogen 1 oxygen kind of composition, and that's where you get the lowest Gibbs energy also, meaning this compound forms, H2O compound forms. So how do we model this? How do we impose it from outside? Associate solution model is used for that. It uses explicit pseudo species H2O. Okay, so this is added explicitly in the model. Therefore, it naturally handles this kind of extreme asymmetry. Okay? So usual sublattice formalism with the RK polynomial cannot do this. Okay? RK power series with regular type of sublattices will have difficulty in handling such asymmetry. Then there is quasi-chemical model or modified quasi-chemical model. It is used for short range order in molten salts, ionic melts and all. In ionic melts, cations and anions must balance, and strong preference for certain cation-anion pairs can happen. Okay, and this kind of systems can be modeled using quasi-chemical model. There is a separate way to incorporate that in thermocalc, and that's what is used for modeling short range order. Okay, thank you. I hope the lecture is useful. See you in the next class.